So select all of the atoms that are in the same plane. I actually technically put this question into the weekly notes thing in a space that I think has a little bit more context. If we're talking about in the same plane, what pieces of evidence would help us to decide if atoms were in the same plane? That's how I break my pen. Okay, so that's taking it to kind of a high level. So if we're looking at that, when you say alkene, that gets a bit misleading. I think you're technically referring to the pi bond. So that pi bond can't rotate. Because it can't rotate, that's going to lock our carbon atoms into that same plane. So we should identify those carbon atoms as part of it. I believe within this function, you have the ability to select bonds. It says select atoms. So if you select atoms and bonds that are all in the same plane, you didn't answer the question, you'll be marked wrong. Does that make sense? So make sure you identify the atoms. What other pieces of evidence could we use to help us to decide whether something was in the same plane or not? Bond angles can be misleading. What is the bond angle in water? So H2O would be our molecule for water. Okay, if we were to draw out, and I'll call a useful drawing for water, we might draw it like that. What's the bond angle for water? So relatively minor point, that is something you should have some fluidity with for assigning. How do we determine bond angle? It's based off the groups of electrons around your center atom. What's your center atom in water? Oxygen. How many groups of electrons are around that oxygen? 4. If we have 4 groups of electrons, that's going to occupy a tetrahedral shape. What are the angles in a tetrahedron? It's 109.5. If we pushed on that a little bit, is it actually 109.5 for water? No. Why not? When we say 109.5, we're making the assumption that all 4 groups are completely identical. Are all 4 groups of electrons completely identical? No, some of those are lone pairs. What does that do as far as the presence of our electrons? In a bond, those electrons are shared between atoms. So if I'm going to share my pen with Josie, the pen is going to move out kind of away from me. If I'm not sharing it, where's the pen? Does it make sense for me to be holding it out towards her? No, that would be a bit silly. I'd hold it closer to my body. Which means if we're looking at non-bonding pairs of electrons, those are held closer to the individual atom. If they're held closer to the atom, that's going to necessarily take those bonds and cause them to repel away from those electrons, which means those bonds shrink away from those electrons. What happens to the bond angle? Changes, yes, do better. Say it again? Wider? If we consider, let's pull it off. Legs, group of electrons. Legs, group of electrons. Bond, bond. Ta-da! Tetrahedral. Who knew I was doing yoga this morning? Okay, that's our tetrahedron. If those electrons get closer to the center of my body, what has to happen to these bonds? Now the distance between all of the electrons, my legs and my arms are getting closer. What happens when electrons get near each other? They repel. So what happens to the bonds? They have to get closer together. If they get further apart, do my hands get closer to my legs or further? Closer. That's bad. That's getting electrons close to each other. So we want to put them closer to each other, the bonds, because they're further out. So the bond angle should shrink. Right? Theoretically, you were taught in Gen Chem, when you look at the bond angle within water, it's not 109.5, it's 105.7. Why? Because not all the groups of electrons are the same. How critical is it to know that number? It isn't, which could be why you've forgotten it. How important is it to recognize that those angles will change? Very. because those changes in bond angles can change where the orbitals for our electrons are located. Why is that important? When we run a chemical reaction, what are we talking about? Moving electrons. And if we don't know where the electrons are, we can't move them. So you have to be aware of some of those kind of repercussions because it will change how reactions, the speeds of general reactions. Okay? So if we look at water or drawing, we say, okay, well, what's problematic about that? There isn't necessarily anything problematic about it, but I could also draw that same water molecule like this. I took that bent shape for my water, and all I've done is turn it on end. Can I see the bond angle anymore? No, it disappears. If anything, that would look like the bond angle is now 180. That's not 180. I would have to know all of those internal shapes. So when we go through and look at this drawing with our A, B, C, D around C, our carbon atom, how do we know where those bonds are located?
The wedge.
Wedge in the dash. What did the wedge mean? It's coming towards you. What does the dash mean? It's going away. What do the solid lines mean?
Same plane.
Same plane. What was the question asking? So one of our it's anything with a solid line. What's the problem with that? Let's take a look at that carbon. I guess for the recording's sake, this carbon up here, green dot, we see solid lines all the way around it. Are all of those bonds in the same plane? No. So the drawing is set up in a way that forces you to make an interpretation. So just because it's solid line does not necessarily mean it's in the same plane. It depends on what drawing format was used. Okay? So why are they providing you a drawing format that doesn't allow you to clearly see which atoms are in the same plane? Because they want you to think through it. What are those spatial relationships? You need to know that. And you have to be able to come to those interpretations. That's why they don't clearly specify them. Right? So, Anthony's point or statement was exactly on point. That's going to be the most relevant. For sure, the carbon atoms need to be, or those two carbons have to be in the same plane. And if we look at the bond geometries around that, those are carbons with 3 groups of electrons, which means we have what kind of shape? Dang, I don't know my shapes. That's where your electrons are located. If you don't know where the electrons are located, you can't do chemical reactions, which we do later in the semester. This is why we talk about them early on, and you now have to apply them. When? Every single structure. And if we have 3 groups of electrons, you started to suggest something? Trigonal planar. Which means if this red double bond is in the plane, what must those 4 bonds be?
Also in the plane?
Also in the plane, because the shape is planar. We can't assume because they're solid they're doing that nicely for us, but what we have to acknowledge is the shape behind our molecule. So that means these bonds must be in the plane. Okay, and I'm going to shift those to now actually be green, and we'll keep our atoms that are in the same plane as red. Okay? Because this question is asking for atoms, I must very specifically identify the atoms. What's at the end of each of those green bonds? An atom. And I'm looking at a line connecting them. By definition, if the line is in the plane, where must the points of that line be? Also, by definition, in the plane. Which means if I'm going to go through and color in atoms, I know these must also be in the same plane. Kind of, sort of? Right. After that, we now start to get tricky. You're like, I didn't think this was tricky yet. This is where it's actually tricky. Right? If we go out, let's take a look at our bottom carbon, our bottom red highlighted carbon. We've noted that we haven't specified wedges and dashes, and we could go through and add that information. Wedge, dash, and then I could keep the other 2 solids. If that is solid, what does that make this carbon? The now very bottom carbon. in the same plane, which should mean, what's the question asking?
Select.
I should select it. Why did I say it was a solid line? How do I know it's a solid line?
Because it's staying away from each other, so.
I specified a wedge for the hydrogen and a dash for the other hydrogen. What if I'd done this? Would that bottom carbon now be in the same plane? No. How is it changing its orientation? Does that change the identity of the compound? No. Okay. How can I just willy-nilly change those around? Am I allowed to do that? Yes. Why?
Because it's not a pi bond to hold in place.
If we look at where those atoms are located, where they are referenced, be it solid, dashed, or wedged, is all in reference back to the original solid connection back to our pi bond. That bond is what kind of a bond? Saw you mouthing it in the back? Sigma. And what can a sigma bond do? Move is a dangerous word. This is moving, this is moving, this is moving. Those are way different actions. Okay? That bond can rotate. Because that bond rotates, can we tell which of those atoms are in the same plane as the rest of the structure? No. So selecting them gets very dangerous. That was my mistake when first attempting this question. I was like, well, one of them is. But I also don't know which one of them is, so I can't highlight any of those. What happens out the other end? The exact same thing. Can I specify which of those atoms are in the same plane or not? No, until I have some more specific information, something that potentially prevents the sigma bond from rotating, all I can say is those atoms in red are the ones that are in the same plane. That's it. That's all I have. Does that make sense? Okay. We can modify this question. What if I drew on a double bond here?
Same plane?
What's same plane?
Are you asking like what would that line be on the
Yeah, how does that change our answer? Yeah. Does it change our answer?
Does it wouldn't? Because ultimately you're pulsing it.
The H would then need to be selected in comparison to the.
Okay, so what we're hearing now is I need to now select that H. Everybody agree? Why are you selecting that H?
Because it's connected to something that's pinned down by the pi bond, meaning that that's not going to be able to move either.
What's the thing that's pinned down by the pi bond?
The carbon.
Is this carbon atom pinned in three-dimensional space? How is it connected to the pi bond?
Oh, I thought you were talking about the.
How is that carbon connected to our pi bond that we've identified? What can sigma bonds do? As it rotates, what would happen to the hydrogen? It would no longer be in the plane of the molecule. Okay? And if you're like, well, what about the other pi bond? Okay, what about the other pi bond? That other pi bond is now going to lock this carbon, this oxygen, and that hydrogen all in the same plane. And then this is where it's going to get real fun. It's also going to lock that carbon in the same plane. But does it force the rest of these atoms to be in the same plane? No, why not? What can that bond do? It can freely rotate. That rotation doesn't change the planarity. Yeah, planarity. I think that's right.
Sure.
Of this system here. All it's changing is where that plane is located. So if we look at this as two different pi systems, we can say two different hands where they're planes. We can look at it where they're in the same plane, but because it's connected by a sigma bond, what can I do? That's still two planes, but are all the atoms in the same plane? Nope, I've knocked atoms out of that plane. So as long as that sigma bond is there, we have rotation, which means I can't lock all of the atoms in the same place. Is it more stable to have this system be the two planes aligned? That's a hard question. Should I have the system where the planes are aligned with each other, or do I want the planes out of whack?
You'd want them aligned
Why do I want them aligned?
to facilitate electron sharing.
Right idea. When we're talking about electron sharing, what we're saying is, whoops, I forgot that I altered that structure. I want to be able to take those electrons and move them there so that I can move those electrons there. That works as resonance because the p orbitals are aligned. That we're using pi bonds, p orbitals. As soon as we do a rotation, what happens to the p orbitals? They're no longer aligned, and therefore I can't pass the electrons through. Okay? It's still a sigma bond formally between it, but there's a more stable state where the entire molecule is planar. We just have the ability for it to rotate. Kind of, sort of?
Question. You said with the oxygen there and the pi bond between carbon, that it's locked in, which I understand, but you said it also makes the carbon-carbon locked in. How does it make it locked in if it's a sigma bond?
It's locked in because that center carbon right here with that double bond is trigonal planar, which means all of those bonds are all in the same plane. So I have to draw a line from this carbon out. That line and that carbon must be in the same plane. How many planes does a line occupy?
When you said locked in, I thought it could still like rotate like hydrogen.
This bond still rotates.
Okay.
As that bond rotates, what changes about the planarity of everything else? Those are all still in the same plane. Okay. What changes in that rotation is that this plane, technically it includes that, and that plane can run perpendicular to each other. Okay? Because that's a sigma bond connecting them. So that sigma identity is what messes up the whole system. Kind of, sort of?
Yeah, you said locked in, I saw like open book stuff. Like I didn't think you said like, oh, it's a really...
All we're talking about is that the atoms in that plane are locked into that plane. The plane can still rotate.
So, say as it refers to the question, you wouldn't select those other atoms then?
I gotta erase everything again. So, in the question initially as shown, carbon, carbon, hydrogen, carbon, carbon. Whoops, hydrogen, I left that one off. Those atoms are all in the same plane. In the modified version, where we drop that double bond, and I think it's a hydrogen out there. For simplicity, I'm going to say hydrogen. Okay? What does that change? Nothing. That's still the answer. Okay? That's still going to be the maximal amount of atoms in the same plane. I'd have to look at that other version to see if they changed the question. I don't think they did. But as soon as you drop in that other double bond, we now have a second potential valid answer. Because we could have said oxygen, carbon, hydrogen, carbon. Those atoms are now all in the same plane. I just can't select those atoms and the carbon alkene atoms at the same time, because that becomes problematic with our sigma bond that connects those two planes. Okay? And quite honestly, I don't know if SmartWork actually has that other answer coded in. I think they're focused on the alkene for right or wrong. Kind of, sort of? We're starting to see that this spatial awareness becomes a really big deal. Hopefully. Okay. What else we should be noticing is that we need practice with this. That spatial awareness is not an easy thing to nail down. That's why you have a model kit. Have you started using your model kit?
I'm going to ask afterwards.
Okay. If you haven't, you're digging yourself a hole because you're trying to blindly move through this system that you don't understand. I asked bond angles, nothing. Okay, so you don't remember anything about bond angles. I asked geometry, nothing. Those are all those shape things that you need to know. If you don't have control over that, you better have control over the model kit so that you can get these answers without having to make those leaps. Otherwise, you got to go back and pull all of the Vesper models and shapes and all that stuff out, and not only know those names, but what they mean. The model kit encodes all of that. That's the value of the model kit. Make sense? Okay. Which is kind of a decent setup for starting the weekly note slideshow. We're going to go through a couple things, hopefully quickly, somewhat depressingly. Questions, comments, we already started some questions. We've already addressed some questions that have been sent to me from email. I've got a couple things to point out also from email. Paper homework. First thing I want to address is if you did not do it, okay, which is going to get addressed again on the next slide. If you didn't do it, paper homework has a late availability, but that late availability means you do more work. Right? That's your choice. I literally had a student last semester that turned in all of the paper homework the week of the exam, because that's when all the assignments were due. That's 2 paper homeworks. Every paper homework late becomes 40 questions instead of 20 questions. So he would turn in 80 questions right before every exam. I go, oh, that's impossible. I don't want to do. You should be doing that. That's called practice. That improves your exam score. Okay? He just decided that that made more sense for him. That's okay. I don't recommend it, but you can do that. The confusion comes in with paper homework 1. How confused were you about the assignment? Somebody will, oh, it wasn't that bad. Well, I'm not talking to you. I'm talking to the 6, 7, 8 other people that didn't turn it in. That potentially didn't turn it in because they were confused. Okay? I don't want to penalize them for confusion. Though arguably we should, because that's why I'm here. You should have sent me an email. Okay? So for the very first homework, there is no late penalty. Just get me 20 questions. Paper homework 2, there is a late penalty. And so this became some of the confusion. If you turn in 20 questions to paper homework 1, great, I can give you points for that. But now you turn in paper homework 2 late. You're now doing 60 questions. Right? 20 for homework 1, 40 for homework 2. So instead of that, prioritize homework 2. Get 20 questions submitted to homework 2. Start working on adding more questions so that you can backfill homework 1. Okay? Because homework 1 doesn't have it's a week late, that's 20 questions. 2 weeks late, add another 20. It's not that. Okay? So it has an infinite kind of due date associated with that. You can turn in homework 1 late as 20 questions at the end of the semester. I'm fine with that. A little bit upset, but I'm fine with that. Okay? Homework 2 has a late penalty, which is another 20 questions. Okay? Kind of, sort of?
Yeah.
Yes, sir.
You said when I checked out the paper homework, there was also you could either do this or do a tutor session or something.
No, that's extra credit.
Is that extra credit only?
That's extra credit. Paper homework is 20 questions, period. Okay? Deciding what to do for it. Okay? It is showing work. Okay? It's slightly more than showing work, though. If you just copy the answers out of the back of the book, I'm not sure our book has the answers, but solutions manual, just copy answers. Did you show any thought process? Did you establish any pattern that would allow you to go, dang, I don't know this? No. The point of the paper homework is to force you to explain it. Why? So that you go, dang, I don't know this and I need help. That's the point. Okay? The rest of it is just you're doing a good thing as a student. Good. Here, have some points. That's fine. You're being good as a student. But now also give you that metacognition to recognize you need help. So when we go through and look at it, we've got 4 potential examples up here. All of these are doing some things right. Okay, I would argue all of these have shown answers. This one here, for the record, I removed names, so if you recognize your stuff, I'm not telling anybody whose name is on it. Okay? Which is the trans isomer? Multiple choice answer. Why is that the trans isomer? Well, because I said it was D. Did you have to draw anything? Couldn't you have just said D is the answer? Does that show any understanding of the concept? No. That doesn't allow any of that metacognition stuff. So what I'll do is I'll give you points, but I'm not giving you points for explanations. You want to maximize your points? Do the assignment correct. Submit more questions to the assignment that are now correct, and I'll backfill those points. Paper homework can be full points at the end of the semester. You can do it wrong the entire semester. All you're doing is now saying, I'm going to do more work. Okay, that's fine. That's your choice. Okay? Let's take a look at the upper left. More work. We have structures drawn out. We've got colors. We've got lines. We have explanation in text. That's phenomenal. That's where everybody should be. Is that a lot of work?
Yeah.
Yeah, okay. You get to decide where you want to be. Do you want to be at that point that's potentially setting you up to guarantee an A? Or do you want to be at something like this? Provide the structure for this. Okay, does this show any work? It doesn't show the explanation, but do I see something as evidence that you know what you're attempting to do? I see some die underneath it. I see a 2. Why is there a 2? I don't need to know why there's a 2. You need to know why there's a 2. I know the answer. Okay? All I want to see is, do you have some thought process getting you to said answer? That's it. Okay? Methyl, 1C, pent, 5 carbon. Took me a bit to figure out why you were drawing a sigma there. It ain't. It means they're all sigma bonds. Okay, cool. That's showing some thought process behind it. For the record, nomenclature is a horrible assignment to do. Okay, for understanding. It makes up the smallest amount of points for our overall exams. Okay, you can crank out homework like no other with nomenclature. Okay, and you're welcome to do that. That's going to shaft you for the exam. That's okay. Again, your choice. Okay, we've got another example up here. There's some words describing it. I'm not looking for a lot of detail. Okay, there's lots of ways you can go through and do it. You're trying to prove to me that you understand what you're doing. Okay? There were a couple other scenarios where they tried to prove, and that was great. But the explanations were kind of like, I chose A because B and C didn't look right to me. So you have no clue? Okay. You at least attempted to explain, but that should be a giant red flag for you. I don't know what I'm doing, and I need help. That's all I care about. I'll give you points. It's now on you to decide to get that help. Make sense? Okay. If I see glaring issues, I will try and point it out. Okay. I'm not grading each question. All I do is look at it, and if I see something that's like, yeah, whoa, that's way wrong, I have to, reasonably say, you got some issues here, you should get some help. And not in that way. Don't laugh at me.
Sorry.
Does that make sense? Questions about the paper homework? Oh, fuck. Okay. Whoops. Next one. Play posit, because there's questions about play posit. Play posit collects points as evidence that you watched the lectures. If they're just YouTube videos, there's no way for me to track that. Okay? So play posit asks questions to kind of keep you active in it, and by keeping you active in it, it forces you to kind of watch it. So I can now track that. So if you watch the video all the way through, you completed all the questions in the video, it's 7 out of 10 points. Sometimes it's higher depending on the next part. Okay? How do you get the remainder points? Well, what I go through is download the flippin' grape, and it looks way worse than this for the record. Okay? Because it puts in all the questions and answers, and I have to delete all that nonsense. But these were questions being scored correct or wrong. That's all these were. So all I go through and do is look at the average for each of those. So some of these, the average for this question was 0. Not a single soul got that question right. So that's the one I should grade. That's not the point. Okay? So what I go through and look is I look at those averages, okay, and I picked 3 scores that were all above 70%. 70% of the class got it right. What does that likely mean about that question? Why did you get it right? You understood it. You mean you were paying attention to the video? Cool, that's all I want. Here's the remainder points. Okay? So when we look at the sum output, look at the scores. They're almost all 10s. Okay? Because the point isn't to penalize you. The point is, are you watching the lectures and are you paying attention? That's it. Why don't I grade some of these other questions? Well, that goes to the intent behind those questions. Sometimes the intent behind those questions is, let's just for giggles, let's make things really difficult. Why not? Okay? Sometimes I'm planting a seed. I know this topic is important and it's going to show up in 2 semesters. That's going to show up when you take biochem. Okay? I don't have to take biochem. Good point. That's why I shouldn't grade you for that question. But for the people that do take it, I want that seed planted so that when they see it in biochem, they go, oh, that's the connection. That's why this is necessary and that makes sense. I don't want to grade that question, okay? But that's why it's there. So don't look at your score in PlayPosit. Your score in PlayPosit is going to suck, okay? And the due dates in PlayPosit, because there's a bug where I can't see the due dates. Literally, I can't see them. I don't understand. It's obnoxious. Okay? So all of those due dates are in Canvas. That's why you're driven through Canvas to get to it. That's how they're graded. Can you retake it? Yes. Okay, which score do I look at? Well, the lowest one, of course. No, I picked the highest one. Again, the point is, are you watching it? So what I'll go through and do is summarize it, and your name will show up multiple times. And I'll see 8, 10, 10. And I go, okay, 10. I'll delete the 8 one. I'll delete the other 10 one. Okay? So if you want to rewatch, go ahead and do so. In general, rewatching costs you a half an hour of time, and you get a point on average, at best. I think the average is actually less than a point back. I think you're hovering about a half a point back. If you want to fight for your points, do it. There's your half an hour, go for it. That's your choice. Questions about PlayPosit? Yes? Submitting the screenshot into Canvas is a paper trail. Okay. Sometimes PlayPosit does weird things. It would be nice if you had a paper trail to be like, Mike, I did it. Okay? And usually what that means is you enrolled in the wrong class. It's theoretically streamlined where that doesn't happen.
But you still see it.
But yeah, I should see it in PlayPosit, and that's how I transfer it across. If I transfer it across and I see that you submitted something and I'm giving you a 0, I did something wrong. So now I'll fish through PlayPosit to find it. And usually what it means is you watched the OChem video while enrolled in the fundamental chemistry class. That's why I can't see it, because of how it's organized on the back end. Okay, so it's only a paper trail thing. Grade expectations. So this is an unfortunate one that we will talk about usually after exams. Let's talk about it ahead of exams. Okay? I've talked to everybody. I believe I've gotten everybody's rough goals on where they're headed and what they do. We've got a lot of pharmacy. We've got a lot of vet. We've got a lot of, what's the other M word? Medicine, PA. All of those are very competitive programs. What grade do you need in this class? A+. Okay. That's what you want. You're aiming for perfection. Okay? So when I go through and say this is when the assignment should be completed, did you complete it by that time? No, you're not aiming for perfection anymore. You're aiming for something lower. Okay? So all I'm trying to establish is what you're aware of, where your expectation, this is what I want. That's what you have to do to achieve that. Okay? Even within that, smart work homework is a skeleton. It is not all the practice you should be doing. You should be doing more. What practice? This is why we have a textbook. Open up the textbook. Start doing practice questions within the textbook. Okay? That's the point of those. You just want to pass, because it's usually, I need a perfect grade. It usually breaks down to, I just need to pass. Right? Don't aim to get a C, because if you aim to get a C, you will screw up. That's life. If you haven't learned that one yet, you're always going to screw it up. Okay? So aim higher so that when you screw it up, you get right where you want it to be. Awesome. Right? Why do I talk about this? Let's take a look at smart work. There are 4 assignments that should have been completed all last week. Let's take a look at our course grade, 88. That's not perfect, so to me, that sounds like people don't want A's. 71, that's really not perfect. 60, that's really 34. Okay, the average smart work grade is sitting at a 64 right now. Like, but it wasn't due yet. I know it wasn't due. What are you aiming for? You figure that out. I'm just pointing at the statistics I can see on my end. Does that make sense? Yes, sir.
Wait, are these the actual?
These are actual.
So,
These are actual outputs from the class. For people who are like, dude, 34% of the class didn't get those right. They didn't complete it, so they're zeros right now. That's why the average is sitting real low on that one. Right? So not starting it counts as a 0 as far as I'm calculating this. So right now we're looking at most people would say not passing average for the online homework. If you want an A, you're in a class of people that don't want an A. Does that make sense? Or if you want an A and you're contributing to any of those low scores, your actions do not match your expectations. Change one or the other. I'll say I want you to change your actions because I want you to have an A. Right? But I'm fully aware that I need to get over that. Kind of, sort of? By the end of the semester, as we push things out, what I decided to do was pull up some older statistics. Right? Homework is a step above completion points. By the end, right, the average grade for smart work is 93%. So when we go through and look at what's going to go into the grade book for smart work, that last week or week of the exam, the score isn't going to be a 64. It's going to be above 90. Right? And I fully accept that. That's going to be there. It'll probably be darn close to 100%. Right? Because we haven't figured out those expectation lines yet. Kind of, sort of? So it is there solely to boost your grade. Give you a little bit of feedback to be like, you don't know what you're doing, you should find some more practice, and then inflate your grade. Why do I need to inflate your grade?
Because this is hard.
Because the exam's going to come through. And the exam average comes in at a 61%. That's curved. Right? I think some of this has to do with people going through and saying, well, I don't need to worry about the smart work because it's not due yet, and doing it right before the test. In which case they haven't learned anything, the test comes through and they skunk it. And not the good skunk, like nothing wrong, they get everything wrong. Right? And that tanks that average. Okay? The only thing you have to do individually and not be perfect on is the exams. Right? I want to address something about this 61% because everybody tends to freak out at this number. What is 61% as a letter grade? No, it is not a D. It's like, what? That doesn't make any sense. That's what I've been taught. You've been taught wrong. What is an average? What letter grade is an average?
C.
C. What is a 61%? A C, because it's the flippin' average. That's what it means. Right? This 61% turned into a C in the class. How does that adjust? You remember all those free points, the homework, the play posit, the paper homework? Those take this curved score and move it up 10%. Are you not doing those? Now you're at a 61. That's not going up, and that stays at a 61. Is that a happy space for you to be? No? Okay, well, there's your expectations. Kind of, sort of? For the record, I find all of that depressing. I don't want to talk about it again. Do you have questions? Good, because I don't want to talk about it. Right? Questions? Here's the one that I wanted. A lot of people are struggling with this question, complete the skeleton, or some variation on it. Everybody I have helped with this question has done the exact same thing wrong. I think one person actually did it correctly, okay, and encountered other issues. What is your step? What is your first step? I want this to go into that skeleton. Step one is do what? Shut your mouth. And if you heard him, keep your mouth shut. If you didn't hear him, then you can chime in.
It's just, I don't know, put in hydrogens.
Okay? Universally, it goes, I'm going to start putting in hydrogens. Okay? When we look at the Lewis structure rules, is that the first rule when we talk about Lewis structure? Just count the hydrogens. When I ask you to complete the Lewis structure for sulfate, you look at the hydrogens. For the record, sulfate is SO4 minus 2. It has no hydrogens. That's not where we start. Where do we start? And now Nick can chime in.
I'm not counting.
That was not the intent of that. Count your electrons. We have to know how many electrons go into this drawing. Okay? That's going to dictate whether we have multiple bonds or not. Okay? That's important. So your first step is to count all of the electrons. I'm sure I'm going to butcher it because I'm not walking all the way through it, but we're going to come up with 46. Something like that. Actually, I'm going to say 45. Okay? And then people will start to count it out. Well, 45 should set off alarm bells. Why should 45 be a problem?
Because we do have pairs.
We do pairs of electrons when we're looking at our structures. We will encounter odd electrons eventually, but they're odd and we tend to forget about them and not worry about it. If you're getting 45, it's probably because you didn't count that negative charge. What does that negative charge mean? There's an extra electron. It's not 45, it's 45 plus 1. We're looking at 46 electrons. Now that you've counted your electrons, what should you do? We already know there's some bonds there. We know those lines represent electrons. We don't want to worry about placing 46 in the whole thing because we already have some accounted for. So subtract those electrons out. I'm going to say 18. Close enough. Okay, 46, 18, 30. What is it? Since you don't know, I'm going to say 34, and we're just going to run with it. Okay, 34. Now what should we do? Okay, and this one becomes challenging. This is where you can split, and now you can go a variety of ways. Did you say 29? This is why you use a calculator. 28. We do horrible on the MCAT. They make you estimate things without a calculator. Okay, so 28. I now need to account for the rest of those electrons. And this, again, is where you can diverge. You can start bringing in hydrogens. I would argue that I shouldn't bring in hydrogens because SmartWork has an extra piece of advice. It says very specifically something about that negative charge. It says it belongs on a particular atom. So I would define that particular atom as a negative charge because that's limiting my whole question. If I place all my atoms around but then set it up in a system where I can't make that atom negative, I've done it wrong. Okay? I'm going to say it was the nitrogen, which it may or may not have been. How do I make sure the nitrogen is negatively charged? Okay, put the negative on it. Is that nitrogen now negative?
No.
How do we know it's negative? Oh, there's a negative sign next to it. How did you calculate that it was negative?
By counting the formal charge.
How do you calculate formal charge?
By valence electrons minus two of the things.
That's a good start.
Bonds
And non-bonding electrons. Right? I see one bond. So 5 minus 1 is plus 4, not minus. Right? So what do you need to do? It's not just minus. How many electrons need to be around there for it to be negative? Did you memorize the bonding patterns that I told you should memorize? You're like, no. That's why you're struggling. You don't have those common bonding patterns nailed down to be able to build this out. You're just throwing stuff at it and hoping for the best. That's not a good strategy. For it to be negatively charged, it should have one bond and 2 lone pairs. Now we have a negative charge nitrogen. Now that makes sense. What should that one bond be to?
Hydrogen.
I could do it to hydrogen or double bond to carbon. Which one's correct? Doesn't matter. Both of them are correct. SmartWork might tell you you're wrong. This is where you can send me an email because this has to do with how it gets programmed in for correct answers. So this is one of those reasons why you should send me an email when you're getting it wrong. Okay? Once that's nailed down, you've now added 6 more electrons, which means my 28 drops to 22. I knew that one. Okay? And now I can start worrying about how do I get those other 22 electrons in there and slowly build it out, build it out, build it out. Okay? So you're working through those bonding patterns. There is one potential issue that at least one of your classmates has identified. If you string double bonds, Because believe it or not, you're going to need some double bonds in this structure. String double bonds like this. Is that good or bad?
Bad.
Why?
Because too many breaks octet.
Where does it break octet?
Because then you have to assume that hydrogen is also connected in there, because we still need to fill in.
How do you imply hydrogens? Number one, we can't imply hydrogens. We're told to add all the atoms. Would there be a hydrogen connected to that carbon? No, because it would break octet, which means, do I draw a hydrogen there? No, doesn't break octet, so not valid. Try again.
Wouldn't it be easier just to add in the hydrogens first?
Tough. What's wrong with it?
So pi bonds can be folded, so they use can be straight.
What are you talking about folded?
With a, I don't know what it's called, less than 180 degrees.
What you're now addressing is bond angles. If I took that green carbon, it has 3 groups of electrons around it, which means the bond angle there is 120 degrees. Not a big deal. When I move to that next carbon, we'll call it the red carbon, how many groups of electrons are there? 2, which means the bond shape is
Linear.
linear, which means the bond angle is 180 degrees. How about that purple carbon?
Same thing.
So what we're saying is that those angles need to be straight bonds. Can you take a 6-pointed ring and make 4 atoms all in a straight line and then have 2 carbons connect them over the top? And what you'll find is that that structure will not physically be able to be built. Do you have the rule set to understand that? Dodgy, real dodgy, okay? Which is why if you did that, you will be marked wrong, because SmartWorks like, there's no way in hell you can't do that. You don't know that. That's why you send me an email. I look at it and I'd be like, you can't do that, bond angles. Here's your points. Because you satisfied the intent of the assignment, you just broke the assignment. Good job. Okay? Kind of, sort of? For the record, did I show the answer? No. Okay, so I don't want anybody drawing that and being like, oh, this is correct. Why is SmartWork telling me I'm wrong? Okay, all I tried to walk through is the basic steps behind trying to get to it. It is a very common one for students to struggle with. I want you to struggle with it. There's that one. Okay, this one comes into play because we're talking about hybridization theory, which is why I dropped the image on here. I don't feel the need to talk through this one again, unless you all want to. No? Okay. But when we're talking about hybridization theory, our big conclusions that are going to come out of that is our shape. Okay? Arguably, you're using hybridization theory to explain why that sequencing of 4 atoms all need to be straight line for a ring doesn't make sense. Okay? It's a bit of a stretch for you, but you could make that argument, and that's why you should know that. P orbitals. Why are P orbitals important when we're talking about hybridization theory? What do our P orbitals do? What?
A lot more room.
I don't know what that means, so I'm gonna say no. Sorry. What do P orbitals do? Why do we care about P orbitals?
We make it so we can't rotate it.
Close, not quite. P orbitals do bring up this concept of rotation as a potential issue, but a P orbital in and of itself does not do that. What are you talking about?
Pi bonds.
Oh, okay.
Okay, the pi bond. P orbitals can be used to make pi bonds. Pi bonds can't rotate because as they rotate, it breaks the connection of the pi bond and we'd no longer have a double bond. So our hybridization theory helps us to address what's going on with that. That's where our p orbitals come into play and how we understand those. We can also use hybridization theory to explain where orbitals are located. Okay? And when we add that information to the next one, molecular orbital theory, we can start now talking about why different reactions work the way they work, okay, with electrons coming in from only one particular angle, because that's where the orbital is located. right? So we need to understand kind of our orbitals to help explain some of that chemistry. Or what we later do is just say, when I see this react, there's two possible outcomes. Right? And that's your choice. That's okay. Do you want an example of that one? Yeah, cool. Let's look at that. Let's make it a little more advanced. I like it. So let's pick.
This is hybridization, right?
It's hybridization and molecular orbital theory. So we look at this structure. How would we name this? This was the thing that everybody was getting like perfect in the smart work. What's that? CCl is the bond, that's not the name. What's the name of this compound? No, you're backing out? You can back out. What's the longest carbon chain? There's one carbon, so I would call that, come on, pen, a meth. Okay, this is going to be the end of my thing. Do I see single or double bonds to that meth? Single, which means my hybridization is ane, ANE. Do I have any substituents on my one carbon chain? I have the chlorine. So we could call it chloromethane. Where is that chlorine located?
Position 1.
By definition, position 1, this is where people get lazy and drop the 1. So we're looking at 1 chloromethane. Okay? Doesn't have to be hard to struggle through our nomenclature, but we got it. Okay? If I were to look at how this molecule reacts, this is going to start to move into this next unit. Okay? What I want to do is look at that structure and say, which of those bonds could break? Okay? And if we're talking about the bond breaking, what we're saying is the electrons in that bond are going to one atom versus another. Okay? So let's simplify. We've got 3 hydrogens, right? All the hydrogens are the same, so let's just look at our 2 systems. Carbon to hydrogen and carbon to chlorine. Which of those bonds do I think should break? Why should the carbon to chlorine bond break?
Because chlorine is very electronegative, so it'll take the electrons.
Okay? Which starts to bring in now an explanation for what we would expect to happen. So if we're going to look at the result for this, we would expect the carbon-chlorine bond to break, so I no longer have the line between it. Where should those electrons go?
Chlorine.
To the chlorine, because it's more electronegative. So I could explain my electrons going out over there. Fantastic. What was the head shake? No? Okay.
We just have to keep going to get it.
Okay. All we're saying is that there's a difference in electronegativity between the carbon and the chlorine. So where would I expect the electrons to go? I would expect them to go to the chlorine. So if I completely broke that bond, I'm now moving beyond what we've talked about because we've broken a sigma bond. That's chemical reaction. As far as we're concerned, we can't do that yet. Okay? Why would it do that? Well, chlorine is more electronegative than the carbon. What would the resulting structure be? We started to fix some of it. The bond disappears, right? And I want the electrons on the chlorine. Would that be an appropriate answer?
No.
Why not?
I mean, you still got to come for carbon for like the formal charge.
There it is, formal charge. Okay? And you said carbon, which made me a little bit nervous. So I'm going to come back. Come on, work with me, pen. I'm going to come back in and remember, say we still had those 2 hydrogens. Okay? You're still right, but you now saying, oh shoot, makes me realize that I think I was seeing what you were going to point out as problematic. We still have to deal with formal charge. So, formal charge me. What were the common bonding patterns for chlorine?
Wouldn't it be negative?
Be negative. How do you know it's negative?
Because it has an extra electron. And then it's supposed to have, I don't know, but then...
So, and that process, okay, having more electrons than it's supposed to have, How many electrons is any atom supposed to have?
Oh, I'm sorry. It's a valence electron shell. Does that work? I don't know.
Okay? And what we're starting to do is take false presumptions based off of patterns, and we're overlaying that on top. Did I teach you to say, based off of it, how many valence electrons it has? No. Okay, so you're deciding I'm full of crap. Okay, that's fine. When the exam rolls around and you get a bunch of questions wrong, I'll be like, remember when I said that you should do it this way? And you're choosing not to? That's why you're getting it wrong. That's okay. As long as you acknowledge that's what you want, that's fine.
It's supposed, yeah, it's supposed to have like 7 valence electrons and now it has 8.
It's to calculate thermal charge. You take valence electrons
Better.
minus the non-bonding electrons minus
Yes.
the bonds,
Yes.
which is what I did. I just didn't say it.
Yes. Exactly. Right? What you are doing in your head, I cannot see. All I can work with is what you write down and what you tell me. Oftentimes, what will happen is that you will not run this process through your head. You run through what you actually said, which leads you to wrong answers later on. That's why I'm very nitpicky about being explicit behind that process. I'm trying to prevent those future errors. Yes?
Is calculating formal charge valence electron minus non-bonding, then bonding, or does it matter which?
Does it matter?
It
It doesn't matter. That math is communicative. So now we have the answer? No, why not?
Should be a positive charge on carbon.
How do you know the carbon should be positively charged?
Because it lost the
It's missing
electron
one.
in the bond.
How many electrons did it lose in the bond, though?
Well, it lost 2, but it only
So as soon as you say but, now I'm going to be like, I have a problem with that. Why is it positive? Okay. So what we're going through and doing is saying, formal charge. Carbon has 4 valence electrons minus the number of bonds. How many bonds does it have? 3. 1. That's why I drew that word with the extra hydrogens. Make sure those were there. 3. And we have no lone pairs, which means 4 minus 3 minus 0 plus 1. Perfectly acceptable. Do you really want to do all that math every single time? No. How do you fix it? What do you need to change to make sure you don't have to do that math? That's good enough. I told you that you need to know your common bonding patterns. If you know the common bonding patterns and you see a carbon with 3 bonds and no lone pairs, that's positive. Done. I don't have to do any calculations. It's there. You have to decide where your threshold is. Okay? Now we have a system. Cool. What would happen if we'd done the hydrogen? Right? We've now broken the bond to the hydrogen. Where do I place the electrons from that bond?
Towards the carbon.
Why are you saying that as a question mark?
Carbon. More electronegative?
Is carbon more electronegative?
I'm going to say yes, just because I know fluorine is very highly electronegative, so I think
True.
it's closer.
What's the electronegativity of carbon?
Higher than
Is problematic. Okay, what's the electronegativity of hydrogen? Is also a problem.
Well, isn't it like a periodic table trend type of thing?
Oh, there's still a lovely trend. Yeah. Okay. But if we're trying to decide which atom gets those electrons, it's not a trend. I need to know the exact values. And if you don't know those exact values, you're dead in the water. Is there something else you could rely on? Yes.
Praying.
You can try praying.
It will not save us here.
Probably not. We're looking at 2 different bonds, right? Carbon hydrogen versus carbon chlorine. Can you tell me anything about those bonds? There's sigma. Good start. Keep going. Oh, say that again.
Carbon and hydrogen are non-polar.
A nonpolar covalent bond, which means which atom takes the electron or electrons? If it's nonpolar covalent, what are you saying? The difference in electronegativity between those atoms is non-existent. Where do the electrons go? I don't know. Coin toss, 50-50. It goes one way or the other. I don't really have a choice. What does that suggest about which bond is more reactive?
It doesn't?
Coin toss for reactivity versus I absolutely have a negative chlorine. You're like, coin toss. Which way do you want to turn? Coin toss, left or right, or someone in the navigator seat saying turn right. What are you going to do? Let's opt for the coin toss. Let's see what happens.
Navigator.
Let's listen to the navigator. We have direct reasons for why chlorine would take electrons away. We have no explanation whatsoever for where the electrons would go within the carbon and the hydrogen. If we understand electronegativity, we can now predict that chemistry. Sweet. Okay? But that requires that we know that carbon to hydrogen is a nonpolar covalent. How do you know it's a nonpolar covalent bond?
I said, like, well, I have the same.
You can do better than that.
Same carbon hydrogen.
What you have memorized is a rule of thumb, that when we have two atoms of identical states, carbon and carbon, that's a nonpolar covalent bond. And you've memorized carbon to hydrogen is a nonpolar covalent bond, which puts us in the exact same category. What kind of bond is between carbon and chlorine?
Polar.
Polar. How do we know it's polar covalent?
Because
Because it's everything else that's not ionic.
Everything else I'm going to call BS on, but that's not those other definitions. Ionic or nonpolar covalent. Are those bond definitions things that you learned about in Gen Chem?
yeah.
Okay, your answer is yes, unfortunately. Whether you remember it or not, yes. Okay? With that information, that can now help us predict how the molecule breaks apart. That's pretty sweet. Okay? And what we're looking at now is how does it break apart? What are the rules that would limit or allow it to happen? So what we've now done is shifted from this system of I don't know what bond breaks to now that bond breaks. The question now becomes how it breaks. Well, we'd form a carbon that's missing its octet. That's not good. So we need something to help it happen. I would need to bring in something with electrons. That something with electrons, interestingly enough, only comes in from the backside of the carbon-chlorine bond. It does not come in from over here. That doesn't happen. Why? So a very hand-wavy answer, which I love, by the way. Okay? I don't want that N with the electrons going in near the chlorine because what's the chlorine? What's the chlorine building? A negative charge. And what happens if that negative N gets near a negative chlorine? It repels. The one that's going to stick is the one that's closer in place. Okay? So where does that N have to go? As far away from the chlorine as humanly possible. That's a very hand-wavy, lovely answer behind that. Can we do better? Yes. If we move into molecular orbitals, what we can discover is that there's an anti-bonding orbital on the back side of that bond. That N is dropping electrons into an anti-bonding orbital. As soon as the electrons are in the anti-bonding orbital, what happens to the bond between the carbon and the chlorine?
It dropped.
It breaks. That's why our electrons come in from the backside. That's why the bond breaks. All using molecular orbital theory. And if you're like, well, why didn't we talk about molecular orbital theory? We did. That's one of those videos we should be watching and trying to figure out. That's kind of the end conclusion of those. That's a challenge to deal with, full disclosure. But that's what's happening within it. There are other ways that this reaction could work. Okay? To change the reaction, though, to allow it to happen a different way, I need to get rid of the hydrogens. I don't want hydrogens anymore. What I want are carbons, and we'll call them CH3s. how does that change this reaction? Well, that negative would still have to come in from the back side. In the previous case, when I had hydrogens, we said, okay, it could happen. Why would adding CH3s now make this potentially problematic? What is the difference between a CH3 and a hydrogen? How is carbon different from hydrogen? Easy answer. One has a C, one's an H. Where you're looking, I completely agree with you do have to make some interpretive leaps, but that look is good. What's the difference between carbon and hydrogen?
I want to say there's a lot, but I mean, say
Start
pH
firing.
balance. I mean, the amount of balanced electrons it holds.
Why would the amount of electrons it holds matter? If I'm now looking at spatially where these bonds are located, they're on the back side, right? And if those carbons have more electrons than hydrogen, what happens is this negative tries to get in there. What does it see? More electrons. And if it sees more electrons, what does it do? It repels away. As soon as I drop in those CH3s, the reaction shuts down. It doesn't work anymore. Unless something changes. What changes? The change ends up coming where it turns out I can now make the carbon with a positive charge. Why would I now be able to make the carbon, whereas before, when I had hydrogens, I was not able to do it? What's the difference now between these structures? That looks like a resonance arrow, not resonance. And it's the exact same thing that you just answered. What's the difference between those structures?
Where the electrons are?
What electrons are you talking about? The electrons on the carbon? That positive carbon has the exact same amount of electrons around it in both scenarios. That's why they're both positive charged. That's why they both have 3 bonds. That is not the difference. Where's the difference? So when we talked about the N trying to come in up here, why did we say it didn't? What was the difference we noted? The carbons caused the N to repel. Why did the carbons repel it, but the hydrogens did not? Carbons have more electrons. If these carbons have more electrons, what can they do to that positive charge? Do negative charges repel positives? No. They neutralize them. Because those carbons are present, they can now share electrons in to stabilize that positive. So it can now come into existence. Neat. We're using electronegativity to predict this. Next fun part, where does this chlorine, or now that chlorine has gone off, now where does our N come in? That N minus needs to react with what? This carbon?
The center carbon.
Center carbon, I accept that. A positive carbon.
This is attracted to the positive charge.
Cool, where's the positive charge? I know it's on the center carbon. Where on the center carbon is the positive charge? No, it's not on that side.
The right side.
The other side, no. Or I could be nicer and say you are only half correct. We're trying to figure out where electrons go, right?
Yeah.
Where do electrons exist?
The orbitals.
In orbitals. What orbital exists for that positive carbon? What is the hybridization of that carbon? sp2, which means we used an s in 2 p orbitals to make the sp2 hybrids. What's left over? A p orbital. What does a p orbital look like? a dumbbell. That positive charge is a p orbital with no electrons in it. That p orbital is on both sides of the molecule, which means where can that N dump its electrons?
On either side?
On both sides. So if we change how the reaction works and we form a positive carbon, we get two possible outcomes where our N comes in from one side or the other, because what's happening is the orbital left behind. If we looked at the other scenario where it could come in from the backside, it's coming in from the backside all at once because there's an empty anti-bonding orbital that explains why that can happen. You're using hybridization and molecular orbital theory to explain those patterns. Or you just memorize. If I see a carbocation, I get two products. If I see it all happen at once, I get one product. That's your choice. Do you want to know the why and how things work, or all you need is the answer? I'll tell you, I'll ask both questions.
This is going to be a stupid question, but as far as the p orbitals go, I know they could either be like this or like this. How would you decide?
P orbitals are always perpendicular to the plane of your molecule, or the plane of the rest of the bonds.
Okay, and since that's forward and backward.
There you go. So until you establish where the rest of your bonds are, you don't know where your p orbitals are. Typically, when we draw a molecule, particularly for a hybridized molecule like this, we wouldn't show wedges and dashes because all of those bonds are in the same plane. It's a hell of a lot easier to draw it like this, where they're all in the same plane. Why did I not draw that one like that? Where's the p orbital on that carbon?
You don't know.
You absolutely know where it is. It's perpendicular to those bonds. Where's perpendicular? Towards you and away from you. Do you think I can draw three-dimensionally? Really? No, I cannot. It's awful. So what I do is twist the molecule, now drop in wedges and dashes, and now I can see the p orbital from the side. So if we understand those systems, we can now apply those systems into advanced topics. If we don't understand those systems, we can't apply it, and we end up having to memorize more. Those are your choices. You get to memorize, or you get to apply. That's it. Which one's better? Neither one's better. I can tell you that I have always taught and learned, or not learned, forced myself to learn, apply. Because I can apply that content now to future classes. If I memorize it, what happens to it?
Disappears.
It disappears. How quickly? Probably 24 hours. Right? That's one of the struggles with OChem. It's a 1-year course. If you try to memorize, by the end of 1 year, you're memorizing an entire year worth of content. You're going to fail at it. Right? Sorry. Right? That's how it works. So you have to find the proper balance between apply and memorize. What happens when you apply? What's the negative with apply?
Gotta work hard.
I think you still got to work hard to memorize.
I have to think.
When, how, time. Application takes time because you have to look at a question and say, how am I going to solve this? Here's what I'm going to apply now or here to build that out. That takes massive amounts of time. You don't have tons of time. Right? So you have to find the balance between those two. I chose to apply, which meant I accepted a loss of a lot of questions because I never got time to get to them. So what I tried to do was decide what questions I could apply faster and then not worry about the other questions because I was going to get them wrong anyway. Make sense? Be unfair to use that clock to end the class, but this clock to start it, so I should stop.